I was going to do today is start on is try to explain something about what's in chapter 20, and which is try to say as much as possible as I can about what the what you can do with the theory of general representations of semi-direct product groups. So there is no kind of, the general theory is way too complicated for us to try to explain. But the what I can do is I want to explain certain cases, and the ones that are most relevant, that turn out to be relevant to physics, and where you can actually get, say, some very general things. And the looking back at how I wrote this chapter, so I should say the last section on 20.4, which is about the representations of a semi-direct product when the n factor is commutative. That that's quite important, and that I'll explain. I'll try to go through the earlier stuff. The stuff in 20.1 and 20.1 and 20.2 is a more abstract point of view on what we were talking about the symplectic group and the Heisenberg group. So I'll say something about that and about why I wanted to do that. There is some detailed calculations in section 20.3, which in retrospect maybe, anyway, they're in principle it's pretty straightforward, but you might kind of wonder why I'm doing this. And the answer in some sense has more to do actually with quantum field theory. I kind of wanted to work out those examples as really kind of the simplest possible examples to get all my conventions right later on when I wanted to apply this to quantum field theory in the second semester. So if you're, so I think the best thing might be to, unless you've got some free time, you might want to ignore section 23.3 now, or if you're taking a look at it and wondering why is he doing that, that's you should be wondering it isn't really very well motivated at this point, and I'll say a bit more about that. Okay, so let me just get started. So what I'll start by going over what we did last time, which was the representations of the Euclidean group in 2 and 3 dimensions. And I want to say a bit more about the relationship to, especially the 3-dimensional case, and the relationship to physics, because that in some sense it's really kind of a central topic in non-relativistic physics. It's really, this kind of story really governs how the free particles with spin, even with spin, behave. So let me talk about that, and then we'll go on to the more general theory. Okay, so let's see. So so just to go back quickly to last time. So last time, so what I was trying to tell you about was what the representations of the Euclidean group in 2 and 3 dimensions, and the basic idea was that to understand this general theory as being to think about what the possible representations of these groups are as the possible kind of quantum mechanical theories of a free particle moving in 2 spatial or 3 spatial dimensions. And then to kind of use everything we know about what the quantum theory of a free particle looks like. Because the quantum theory of a free particle comes with momentum operators, which tell you how to translate. And it comes with rotation, with angular momentum operators, which infinitesimally tell you how to do rotations, either in 2 or in 3 dimensions. And that package of information is exactly what you need to get a unitary representation of these groups. And it turns out that if you enhance this case with some ideas about spin and higher angular momentum and an internal angular momentum, then you get all possible representations. So quickly in E2, and then the other thing to say is that always in all of these cases, there's always some more trivial representations we're not interested in, which are if the translations act trivially, then your representation is just a representation of SO2 or of SO3, and then you just get the standard finite dimensional ones you already know about. So we're interested in representations of these guys where the translation group subgroup acts non-trivially to make the problem more interesting and not trivial. Okay. So
question here.
Yeah.
Oh, do you mean by translations act trivially on a representation?
Yeah. What do I mean? Just that. I mean, so you can find okay, so you can. Well, so we want so we want reps where translations act non-trivially, and which really just means that the corresponding infinitesimal translation operator is that p the p vector these things on psi is not identically zero. Or I mean, another way of saying it physically is there's kind of a sub. Well, is that you could instead of looking at all instead of looking at all these, I guess if you just take if you just look at constant, So if you just look at the momentum zero subspace of your theory, or the theory where all the wave functions are constant, then those constants you have a anyway. Then you've got a much simpler finite dimensional problem, and you get some things which are technically irreducible representations of the group, but they're not really they're not the ones we're interested in. Does that help at all? Does that answer?
I mean, the wave function is a constant, which is the case where momentum is zero. Then the translations acts on these wave functions trivially. Is that because they are translational invariant? Yeah.
So being constant.
So in this case, acting trivially means that if you act on the wave function by translation, it doesn't change this wave function.
Right. Yeah. And so in some sense, I want the case where the wave functions can vary in space. If the wave functions are just constants that don't vary in space, then I'm really just looking at SO2 or SO3 representations on the complex numbers, and then there's nothing. Then I'm not getting anything really interesting. I mean, this wasn't meant to be an interesting comment. It's meant just to be a purely technical comment. That at some points I want to say that these are all the irreducible representations, and there's kind of a technical comment that I don't. There's also these kind of. There's also the ones that are just representations of SO2 or SO3, and those also. Those also are representations of the bigger group if they're trivial on the translational part, but it wasn't meant to be an interesting comment. Okay, does that help, Jen?
Yeah, I just wonder, it's kind of different from the problem in the homework, because in the homework we are asked to show that the second Casimir operator acts trivially on the E3 representation.
Okay, well,
which I think that case actually gives you zero.
Yeah, but that's the second Casimir. Okay, actually, let me come back. Let me say something about that, because I'll get to that in a minute about the second Casimir. Let me explain that. But yeah, it's the second Casimir. So saying the so I'm not saying anything about the Casimir operators. I'm just saying something about what happens when you translate. Casimir operators are kind of second order things, and even when you have a Okay, yeah, let me get back to that when I come to that in a minute, because I want to say a bit more about that second Casimir operator and what it's doing. That's kind of the whole point of the thing, which I may have just said a few words about it at the end of last time. I don't want to say more today. Okay.
I think what you're saying, there are two kinds of acting trivially, right? Like here, this acting trivially, it's actually the identity operator, whereas the acting trivially is actually a zero,
Yeah. So always, so when you say that you have a trivial representation, if you're at the level of the group, that means that the group, all the group elements are acting as the identity. But at the level of the Lie algebra, remember the Lie algebra is the thing you exponentiate. So at the level of the Lie algebra generators, the Lie algebra is acting as zero. Okay.
Oh, I see.
Okay. Yeah. So depending upon whether I'm talking about a Lie algebra action, if it's a Lie algebra action, then everything that generates the the action of the Lie algebra on the representation is going to be zero. Zero means that it's acting trivially. At the level of the group, e to the I times those generators, that's going to be act as the identity.
But here, like the momentum operator, this is in the Lie algebra level, right?
It's the Lie algebra, yeah. So it's zero. So we're looking at, so when I say that the translations act trivially, I said, in physical terms, that means that we're looking at zero momentum states.
Okay.
So, or yeah, and if you think of the momentum as a derivative operator, we're looking at constant states. Okay. Okay.
Okay.
Okay. Okay. So let me go, and then so let's go on, and then to the okay. So quickly about E2. So what we do is we work with the free particle theory. We look at the representations on H is L2 of R D. Well, so D is two or three, and then the simplest behavior, since we're the momentum operator is the main thing. What you want to do is you want to go into work in momentum space. Then this becomes just a multiplication operator. So we're going to take our as elements. We're going to think about our wave functions, but we're going to work not with the wave function as a function of x generally, but with the wave function as a function of p. And we can always Fourier transform back and forth. But if we work with the wave function as a function of p, then the translation operators just act by multiplication on this, and so it's a lot easier to see what's going on. And then what you find in the in d is equal to 2, the irreducible represent. So the irreducible representations are given by let's say psi tilde of p vector is equal to so is some function of so it's given by some function of theta related at a delta function of where the size of p vector is something, and to give it a physical significance, you can think of these as being solutions to the equation for a free particle of mass m. Then you would say it's that this guy is square is equal to 2 me. Okay. So in other words, that if you're in momentum space, then what you've got is your a general wave function is going to be a wave function of whose Fourier transform takes different values anywhere in momentum space. But if you want to find the irreducible representations, what you do is you just you pick something of some radius, and then then this is, and then just parameterize the circle by theta, and the distance here is what I was calling square root of 2 me. square root of twice the mass times the energy. And so this is going to be, so if you write down a wave function that's of this form, it's a distribution which just takes values on here, and it's some function depending on theta, and it's just localized on the circle. Then what you find is that you've got anyway, you can see what's going to happen is that, well, anyway, you could then go and write down what p vector and l vector, what translations do to this, or to these functions, and you can write down what rotations do to these functions. They just rotate you around the circle. And I kind of wrote all that out in detail, and so then you can get see how the whole group EV2 acts on these functions. And as I think I said last time, somebody asked, it's a little bit more of an argument to show that this is actually this representation is irreducible. It doesn't break up into, doesn't have any sub-representation. And this is them. So these are characterized by the eigenvalue of this p vector squared. So just the sum of the squares of the p1 squared plus p2 squared, and that's this that's this guy. Okay, and this is a Casimir. Okay. Anyway, and so, but it turns out, but this is really pretty much completely the end of the story for the Euclidean group in 2 dimensions. That the irreducible representations are these things you already know about. They're the momentum space the momentum space representation for a free particle, and they break up into a continuous set. There's a kind of continuous labeling of a set of irreducible representations just given by this radius here, which can go from 0 out to infinity. If you fix that, you're also fixing the energy. And so if you look at the wave functions of a fixed energy E, then you're going to be looking at wave functions of this kind in momentum space, and you can work out what E of 2 does to them. It gives an irreducible representation, and the fact of the matter is that's all there is. That's the end of the story about irreducible representations of E of 2. Okay, so this is. So are there any questions about this, about E of 2? Okay, so it gets more interesting in D is equal to 3. So you do, part of the story is pretty much the same thing. That what you want to do is, so it's the same as D is equal to 2 with psi tilde of p vector is now, so now instead of a circle, you've got 3 dimensions. So you've got a sphere, and you've got a, but it's the same, pretty much the same story. And but psi tilde is something that's, if you want an irreducible representation, it's going to be given by some function on a, you set the first Casimir to some p squared to some positive number, and then you get a sphere of that radius, the square of that radius, which is square root of 2m times the energy of the state in momentum space, in the sphere in momentum space, and then you look at all functions on the sphere. Let's say it this way. Delta, same thing. And then so this gives you, so you get, anyway. So this gives you very similar representations to these guys, except that they're anyway, instead of being functions on the circle, they're functions on the sphere. The irreducible representations are functions in the sphere, and you can, and the way rotations act on these things is a little bit more complicated. You're rotating a sphere, not a circle, but it's pretty much the same thing. Okay, but what happens in 3 dimensions is that this class of representations labeled by a positive number E is is not all the irreducible representations. It's only part of the. It's only one of. There's an infinite set of different kinds of representations, and so and that's what this is. This comes back to this question about the second Casimir. Let me say some more about that. Okay. Okay. So what happens in so now the other stuff in 3 dimensions. Yeah. Well. So what's in B is equal to 3, you have more possibilities. Okay, and and there are various ways of labeling these other possibilities. So one point of view is there exists a second Casimir operator. And so, and sometimes we'll write it, what it is instead of taking the momentum, the momentum operator dotted with itself, you take the angular momentum operator and dot them with P vector. So it's whatever your angular momentum operators are, dotted with P vector. And I just want to say this. And if you think about what this is, so what this is, so remember you've got, so L vector is the thing that tells you how to, it tells you how to do infinitesimal rotations of the system. Okay, so L1 tells you how to do infinitesimal rotations on the around the first axis, L2 around the second axis, L3 around the third axis. In some sense, if you're looking at a momentum eigenstate, then L vector dot P vector is going to tell you. So on a momentum eigenstate, with eigenvalue P vector. This L vector dot P vector is the generator of rotations about P vector, or maybe I should say it's better maybe to normalize this by this way, so that it doesn't depend upon. It only depends upon the direction of this, not the length. Okay. So you can check that this is a Casimir operator just by computing its commutation relations with P and P and L and showing that it commutes with everything. So it has to it's by Schur's lemma, it's gonna, if it commutes with everything, it's gonna act as scalars on irreducible representations. And so one thing that's true is that on reps on L2 of R3, we've seen L P vector psi is 0. Okay. So that's what I was asking you to show in the problem set. I think in the problem set you're being asked to think about what is what exactly is this operator, and let's compute what it does on all of the on our wave functions, and what you should be able to show just by, because you know explicitly what these things are doing, you should be able to show that on if psi is just some kind of function on x, or the Fourier transform is some kind of function on p, then it's going to be it's going to act as zero. Okay. So what's going on here really is that you've got this other possibly interesting Casimir operator, and you know that what it actually, it also has an interesting interpretation. It has an interpretation as being the generator of rotations about p, and this is an SO2 group. And what you've shown is that the representations that you already knew from the free particle, the standard free particle, that these were kind of invariant. These were all kind of invariant under these rotations around p vector. That they're not actually so the second Casimir isn't actually telling you anything new. But since the second Casimir is the it's, as far as the Euclidean group is concerned, it's a second order operator in the Lie algebra. But it does generate an SO2 group, this group of rotations around the p vector. So what you can do is you can say, well, wait a minute, but it's possible to find representations where L vector, not p vector, over p vector, or if you like, the square root of the Casimir is is non-trivial, is non-zero. And since this thing generates an SO2 an SO2, and you know what the SO2 representations are labeled by an integer. And they'll be labeled where they're labeled by an integer, n, which is the rep of this guy, and this is called the so the name for this is the helicity. So what we'd like to think about is, can you find some way of constructing representations of E of 3 of the three-dimensional Euclidean group where that have non-zero, so-called non-zero helicity, and which means that this operator acts non-trivially on them, and by this argument we expect that this operator divided by the square root of p squared should act as some kind of integer, and it's going to have the physical interpretation of telling you that there's something non-trivial that is happening in for these representations when you rotate around the axis given by of a fixed for a fixed momentum eigenstate. And now, so to get these, so you consider free with spin s. Okay. So far what we talked about, whenever we talked about free particles, we always meant what more generally is called a spin zero particle or a scalar particle. So when somebody says that you're looking at elementary particles and they're scalars, what they mean is that these things transform trivially. They're the S equals 0 representation. They're invariant, and everything is invariant under anyway, maybe it's better to say just what we've been looking at so far, which is just functions on the on R3. Those are what are called scalar scalar particles. It's just that we're taking the functions are just scalar functions. But what you want to do, so what you do is you take H to be L R3. So you take your functions, and then instead of taking functions on R3 with values in the complex numbers, you take functions that take a value in some irreducible SO and some SOD SO3 representation. So so one way of saying functions on R3 with values in some SO3 representation is to take it as the tensor product, and let's take, instead of just taking them with value in C, let's take it with the take them so that they have some values in some irreducible representation of SO3. So, or spin 3, because it turns out all of this story is really a Lie algebra story, and it you can work with the either SO3 or its double cover spin 3 if you either way. So this would be 2s plus 1. Okay, and then what happens is that the generator. So then the way the group is going to act on these things is the group is going to act. The translations are just going to act as the p operators on here, just the way it's the usual story about momentum. And these degrees of freedom just go along for the ride. But if you do a rotation, so rotations act by, so on they're the usual infinitesimal rotation operators here acting on, just by as the rotation of coordinates in here. And it's the thing I've been calling L vector. This is the Lie algebra representation of rotations on these guys. But what you can do, remember that when you take, if you have a group acting on a tensor product, what you can do is when you take the Lie algebra, you find that you get this guy, and you have the group action here and here. Here it's going to act by the usual rotations on coordinate on your spatial coordinates. Here it's going to act by the spin S representation on here. And so that, remember what happened when you had a group action on a tensor product. When you looked at the Lie algebra, you had this guy. You had two terms. One where you act here. You act here, and then you don't act here. And maybe this may be a kind of a bad notation because it's again it's confusing. I want this, or maybe I want this to be the trivial Lie algebra representation on here. So maybe let me call it better to call it 0, and then plus the thing which is 0 on here, but acts non-trivially on here. And so these are what are called the let me just call these the spin operators, but they're for for spin 1/2, it's just, these are just the Pauli matrices, but in general you have it's whatever the operators are that generate the that are appropriate to the spin S representation. Okay, so anyway, so this is physically how you can actually get at get at these more general representations. Is physically you just say, aha, well, let me just enhance my theory of free particles to a theory of free particles with spin. So free particles that have this kind of, the rotations also act on this degree of freedom. And if I take 2s plus 1, then what's going to happen? Okay, so this is an irreducible representation of SO3, this guy. But if you look at what the Casimir is doing, the Casimir is picking out the second Casimir is picking out an SO2, and it's here. Remember that whenever we looked at spin representations, we analyzed them by taking by picking an SO2 and then decomposing according to the weights under that SO2. But what we're going to do is we're going to do the same thing. So you can, so here, so to get, so this thing is not irreducible. Even if we fix the first Casimir, we're still going to have several irreducible representations. But to get here, what you want is you fix P squared, but you also fix. So this is this acts by 2ME by NE, and then you fix L vector dot P vector acts by N times P vector, and so and there's a and the possible values of our N. So since this generates vector dot P vector over P vector generates an SO2 sub 3, and you got that N. So N is the weight of this SO2 action. That was the name we had when we were looking at SO3 representations, and we decided to analyze them by picking an SO2 inside there and seeing what that did. And then we found that we got integer eigenvalues, and we called that the weight. Well, same thing is going on here. Except it's this guy that's generating the action of this SO2 subgroup. And what you find, so you find irreducible representation of helicity, the minus S plus 1 minus 2, well, it's minus 2s. What happens when we plus 2? Now what happens? So minus 2s plus 2 up to 2s. And so they're going to be 2s plus 1. Possibility to just with one. So if you do this construction that I suggested, is that you start thinking about not just scalar particles, but you start thinking about particles with spin s. Well, what you get is you get a whole new you get a whole new list of possibilities for each s, but they're not. And within the things you've created, the irreducible, you're going to get irreducible representations if you just stick to the subset of this where this operator acts by a specific weight. So the and those weights are going to be the N. Okay. So the N, if you ask the question to a mathematician, what are the possible representations, are going to say that, well, they're going to be labeled by a positive real number, and they're going to be labeled by an integer. And if you ask, how do you construct them? Well, if you want to construct, you just look at a free particle with energy E, and then if you want to construct a representation with helicity N, what you have to do is just pick a particle with spin, and take the spin s big enough so that in the list of weights, n is somewhere in this list, and then you just you construct something which is kind of too big. It has lots of different helicities, and then you pick out the piece within there. You pick out the piece where the helicity end. Okay. And so later on in this class, I want to talk about the case of spin 1/2. And so maybe just to say that example. So the simplest example is S is equal to 1/2. And then what you take is you take H is equal to L2 of R3 cross C2. So instead of having your functions take values in C, they take values in C2, and then you have the usual angular momentum operators, which don't touch this guy, and then you have spin angular momentum operators, which are just the so S vector is just the Pauli matrices over to acting on this guy. And then the Hamiltonian is actually given by 1/2m. And then it turns out what's interesting about this theory is you can write it as sigma vector dot p vector squared. And so the usual Hamiltonian, which is the usual Hamiltonian actually has a square root then, which is you write it in terms of a matrix acting on C2, and it has an interesting square root. So we'll talk more about that later. But this is the case. N is equal to 1/2, and here you get irreps of helicity. Oh, well, the way we got it, helicity plus or minus 1. So if somebody asks you how am I going to create an irreducible representation of the Euclidean group in 3 dimensions with helicity 1, let's say, well, you would say, well, take the theory of a spin 1/2 of a free spin 1/2 particle on R3, and then just pick out the spin up piece of it. Or no, sorry. Pick the part of it where where L vector dot P vector pick the part of it where S vector dot S vector dot P vector find that's going to have eigenvalues plus or minus the size of P, and then just take the plus 1 if you want. This is a plus half, or take the minus 1 if you have this minus half. Okay. So I think that's pretty much the end of this story that I want to tell. Is there any questions about E2 and E3 and about? But this is really the end of it. This is all there really is to say about irreducible representations of E2 or E3. This is the complete list. Yep. So what I wanted to do then, the next thing I wanted to do was to go on to do something much more abstract, which is to kind of use this as that what we've done is a special case of a much more general class of groups. And then, for this more general class of groups, it's actually possible to use the same techniques we used here and to get the complete list of irreducible representations. So let me start on this general theory. Okay, so more generally, let's ask about the irreducible representations of n semi-direct product K, and what we're going to make special about this is that n is commutative. Okay. So in general, there's no reason that n should be commutative. For instance, in one case, the so-called Jacobi group we're looking at, n was the Heisenberg group, and this was a symplectic group, but that's much harder. But here, what you can do with it, things are a lot simpler if n is commutative, and this was true for E2 and E3, because then in E2 and E3, n was just the translation group R2 or R3, that it was a commutative group. So more generally, let's take n to be an arbitrary commutative group, k to be pretty much an arbitrary Lie group, and let's actually ask, how would we approach this problem of finding irreducible representations? And one reason for talking about this is that I want to first what we're going to do is we're going to study. We'll look at of n. So first, so we're going to forget about k for a minute, and then just say, okay, well, we got n, and all we know is that n is a commutative group. What are the irreducible representations? Okay, so you've already seen this for n as r and for n as u1, but more generally, what you do know is so they have to be one dimensional. So remember that we gave this argument way back at the beginning, that if you had an irreducible representation of a commutative group, it has to be one dimensional. Okay, but let's do let's make a definition. And so for n commutative, this doesn't really matter whether it's a Lie group or a finite group or an infinite discrete group, also anything as long as it's commutative. Then and so if you put a hat, this is the set of, and so to give it a name, it's called the characters of n. And let's just say it's n foot. The set of characters of n is given by functions alpha n goes to c, such that that satisfy this homomorphism property. Alpha of n1, n2 is alpha of n1 times alpha of n2. Okay. So what we can do, if we want to, if somebody has this a commutative group, one thing what we can do is we can look at the functions on the commutative group, functions alpha, and then we can say that, okay, I want to look at very special functions. I want to look at ones that satisfy the homomorphism property, and that's going to, and so that they satisfy this property. I want to pick those up. Okay, and these, it turns out these, so n hat is a group. The set of these with a group law, so alpha 1, alpha 2. So you can multiply two characters and get a third character, and the third character is just going to be the function that's just given by the multiplication. Alpha 2. Okay.
So from this definition of alpha, it looks like it's not necessarily unique, right?
No, yeah. So this set will have, so there are many different sorts of n's that will do this. So one thing that will always do this is if you just take the identity map, just take the thing which to every element of n just gives you 1. That's always going to work. So it turns out, so n hat is a group with, that alpha then is equal to 1 is the identity element. But it's also got but it's got lots of other possibilities. And the examples are, that you've already seen, is that n is equal to u1. That you have that the character group is z, and for n is equal to r, the character group was equal to r. Okay, sorry. I guess I should also have actually. I guess to make this work out correctly, I actually want unitary characters. So I want this as actually I want to take alpha as so I don't want just arbitrary complex numbers, but I want complex numbers of yeah. So if I don't say this, I get what are kind of arbitrary characters, but I want what are called unitary characters, ones that this function, always has length 1. Okay, and then you have this. Yeah.
How is the character here related to the previous definition of the character of representations,
Okay.
which is the trace of the matrix?
Yeah, it's not. So what's the character?
Yeah. Guess it's in chapter 9 where we use that while character formula to.
I'm trying to see. Yeah. So
composition.
the other character. Yeah. So it's a somewhat different use of the word. In the thing that what you're asking about, you were using this. Okay. Yeah. So the right way to say it is that there's a more general notion of the word character, and if you want to know the character of a representation, you're getting yeah. Actually, maybe it's better not. It's better not to. There's not that much. There's not. They're really different uses of the word. There's some relation, but they're different uses of the word. So that was the character of a. I was applying that to the case of not non-abelian groups, where you have non-commutative groups. So if you have non-commutative groups, then you had these matrices, and you could take their traces, and you got the character function on the group. Here we have commutative groups, and so I guess it's true that the character of an irreducible representation as the trace of a group defined that way is the same thing as the character that actually gives that on a commutative group, the character gives a one-dimensional representation. The character of an irreducible representation gives you the one-dimensional representation. So there's a relation there, but it's not by definition they're two different things, but they're related. They're related when the group is commutative. Okay. Okay.
So in the case of commutative group, the trace is just the simplest characters there, because you have all one-dimensional matrices and
right. Yeah.
take the traces themselves.
Yeah. So the trace is just the the trace of a I mean the trace is the element itself. So it's not in that case. So that gives you a relation with this, but I don't know if that's so useful. But okay, and so maybe the examples here are here these functions were labeled by z, and remember so here we had alpha sub n of theta is e to the I n theta, right? So the example, there's an integer characterizing these people, and that's a and again, so what you should notice is that the character group actually is really, if you look at this definition, for irreducible representations which are one-dimensional for commutative groups, the character group is actually I should actually say this. So the character group is really the same thing, is the set of irreducible representations. It's really the same. Anyway, these things give you irreducible representations, and all irreducible representations you can find this way. So and there's a lot more to say about this general theory, which I kind of don't want to get into too much today. But these things are also kind of interestingly dual. That if you take, so you're starting with a commutative group here, and you're getting a new commutative group here, the character group. So you can ask, what's the character group of the character group? And it will take you back to this. So the character group of Z is actually U1. And then this is a self-dual situation where the character group of R is a character group of R. But the characters here are the things that we would label by a P, and depending upon Q or whatever, they're just the e to the I P Q. So these are in these cases, these are things you've already seen before. But this is an abstract definition which actually works for any commutative group. Okay, let me see. Okay. So now what do we do with this? Okay, so this is pretty much all there is to say about. It's just I want to talk about the representation theory of a commutative group. All there really is to say is that there's another commutative group, n hat, which you can define this way, and that the elements of this correspond to all the irreducible, to the set of irreducible representations. Okay, so and in particular, we're interested in, well, okay, the cases we've looked at, n was R2 or R3, and the n hat was also R2 or R3. It was just you just went from position, functions of position to these characters labeled by the momenta. Okay. Okay. Now what about now? If we have now we put this commutative group into a semi-direct product with this other group. So what we do is we have the information that we use to construct this thing is for each k a map, an automorphism of n, a map from n to itself that preserves the group law. So we have for all k element of k, phi k, such that n goes to n, and it's a homomorphism. Right. So this is by definition the data of what we have if we have a semi-direct product. Then what you can do is you get, so this gives this gives a map, an action. So this is an action on a set on n, and whenever we have an action on a set, we can look at the induced action on functions of the set. This gives an action on functions on n. Which is the usual way that actions on a set give you actions on functions in the set. And then what you do, but in particular on the functions alpha element of n hat. And so what happens, and this is going to be, so alpha goes to what I'll call, alpha goes to phi to k of alpha. Let me call this, well, I'll call phi sub k, I'll call this the hat action on alpha, which is the alpha satisfies that the so the action on alpha gives you this guy, which is the thing which, if you look at, he's a new function, and if you look at what his value is at n, it's alpha at phi k inverse acting on n. Okay, so it's just the usual induced action on functions, but it gives you an action on takes elements of n hat to other elements of n hat. Okay, and anyway, let me try to say the rest of this a little bit quickly. So we get an action. We get a map. We get an action of K on the set n hat, which is given by this guy. And in the example of E of D, then n hat is RD, and this I work out in the notes. You can check the details there, but you can figure out what's going to happen. So these guys are labeled by p vectors. So these guys are really just the momentum eigenstates. That's the irreducible representations of the translation group, and then phi hat acts by rotation. The p vector. Okay. So anyway, anyway, this is kind of what you expect, that in the case of the Euclidean group, the action of K on Rn is the rotation action. So when you look at what it's doing on the character group, it's just doing rotations. You've just moved from Q space to X space, so you're still just doing rotation. Okay. Okay, so then now let me tell you the general story I want to, then the general theorem. Okay, so given a representation of n, let's call it pi v of n k. So what we can do is we can look at, we can first decompose this representation according to how n acts. So let v sub alpha sub v sub b be the subspace where n acts by the character for alpha. Okay. Or if you like, in the example we're always thinking about for the it's just the momentum p eigenspace. Okay. If n was a translation group, then this is just the these alphas are really just the p vectors, and we're looking v sub alpha is going to be the momentum, the eigenspace with momentum p vector. Momentum, yeah, p vector. Okay, then what we can do is that so claim this is worked out in the notes, but I won't try to prove this here. Is that if you start with something in this eigenspace, then and then act with 0 here and k here, or maybe it's instead of 0, it might be better to think of this as the identity. Well, it's 0 in the rotations, or the identity in here, if you like. Then v. What happens is you move. You can compute what n does to something like this, and using the homomorphism properties, you could show that this is a this lies in the okay. So you get moved around from one eigenspace to another eigenspace, and the way the eigenspaces change is just that k acts by this automorphism on the characters, or if you like, if you have something in the p eigenspace, you act with an element of this, where you don't do a translation, you just do a rotation. You're just going to move into the you're just going to rotate the p vector to a rotated p vector. Okay. And so what happens is that you get if somebody hands you one of these, a representation of this, what happens is that you're when you start acting, you can analyze it by looking at the way n acts by decomposing according to characters, and then you can look at the way k acts by saying that k is then going to move you among. It's going to rotate you around these different these different eigenspaces, or these different characters. So you get you get an orbit in n hat, where k takes you to the orbit of all the so you get an orbit of, so given maybe sorry, the story starts to get a little bit complicated, but so for each alpha element of n hat, you get an orbit what I'll call O alpha, which is all the things you get by acting alpha. So if you act for all the different k's, you act on alpha, you're going to get some orbit. And the examples are really exactly the ones you already saw in 2 and 3 dimensional Euclidean group. These were the circle or sphere in R2, R3. So the thing to think, if you think about the specific example of the Euclidean group, then n is R2 or R3, and this guy, these orbits are just, if you pick an element in R2 or R3, is a specific value of the momentum, you just rotate among all. You're just rotating that vector around and getting a circle or a sphere. But more generally, if you do this for an arbitrary thing, in general, I don't know, for each alpha element of n hat, you get an orbit. Okay, and then the problem. Then what happens? Okay, then you can characterize the irreducible representation. So, okay, and then at each, so that's one part of the story. But then remember what happened when we were in the case of E3, we found that if we were at a particular point in the orbit, at a particular momentum vector, that there was a subgroup of the rotation group which kind of left that vector alone. So for each alpha element of n hat, there exists a subgroup, k sub alpha, sub k, of elements k such that phi at k alpha is equal to alpha. Okay. So in other words, there's some that, in 2 dimensions, if you pick a point in the circle, every kind of rotation will move it to something else. In 3 dimensions, if you pick a point in the sphere, there was a subgroup of rotations which rotations around this axis that leave it alone. But okay, and this is called the so this is called the so K alpha is called the stabilizer group. Of alpha, or there's also another standard terminology in physics is this called the little group. Of alpha. Okay, so then what okay, so then at this point I at least have the information that I want to use to actually tell you what the answer to the problem is of classifying the representations. I don't takes a bit more work to go into proving this and to thinking about how to construct such representations. But let's say this is that the irreducible reps of n k are labeled by 1 an orbit of k on that. Okay. And so this is that circle or that sphere in the case of the Euclidean group. But then the other thing is that an irreducible representation so let's call it O sub alpha. Irreducible representation of K sub alpha. So in the case of this helicity, remember, I found that the way the representations corresponded to knowing what an orbit was, to knowing the first Casimir, to knowing the momentum squared, but they also corresponded to knowing to picking an irreducible representation, the helicity, an irreducible representation of the SO2. Well, the same thing happens in general. It's just you figure out what the possible orbits are. You figure out what the possible orbits are of if you look at how phi k acts on n. And then once you figured out, then for each orbit, you look at it and ask, okay, what's the subgroup that preserves, what's the stabilizer group? And as you move around in the orbit, you're going to the stabilizer group will conjugate inside the bigger group, but up to conjugation, it's the same group, and you want to ask, then you ask, let's pick an irreducible representation of K alpha. And that's going to be this is going to be an analog of the helicity. Okay, but as K gets bigger and bigger, you have to these K alphas get bigger and bigger, and you have to say something. Anyway, so you have to use more and more representation theory. But in the case of E3, that K alpha was SO2, and we knew what to do. Okay, so let me just do a couple quick examples. I think so. I won't get to the other thing, but let me. An example. So some other examples are so. For instance, the if you wanted to go to higher dimension, let's say you wanted to know ask what are the representations of the Euclidean group at higher dimensions. Well, it's going to be the same thing. Is that you get so the irreps are labeled by. Well, it's going to be the same story. You have an RD, and you've got rotations in d dimensions, and the orbits. If you pick any element in d-dimensional space and act on it by rotations, you get a d-1 dimensional sphere. So irreps are labeled by 1. The S d-1, or the radius of orbit. S d-1. Okay. And then if you ask what's the subgroup of SOD that leaves invariant any particular vector, well it's the rotations in one dimension or less. So it's the stabilizer groups is always SO d-1. So irreps are labeled by you have a irrep of SO d-1. So they're going to be labeled by two pieces of data. One is this non-negative real number, or non-zero, it's positive real number, and the other is an irreducible representation of the rotation group in one dimension less. So for us, so we already saw this for here. We had the helicity was integers for SO2, for SO3, but let's say that e.g. for d is equal to 4, K alpha, the stabilizer group is SO3. And so you get so that's labeled by 0, 1, 2, but not by arbitrary integers, but by natural numbers. So this is the spin, and depending upon whether you want to look at SO4 or its spin double cover, you're gonna if you look at the double cover, you also get the spin 1/2, the half integral spin things. But otherwise, you just get the spin. And if you want to go to higher dimensions, then you have to learn about what's the representation theory of the higher dimensional SO3 groups, SON groups. So you have to think about SO4 is pretty easy because it's really two copies of SO3. SO5 starts to get to be more interesting, and there's a more complicated story. But once you know the representation theory of the SOD groups, then you've got, you know how to label all the irreducible representations of these ED groups. And you can always give these things kind of a physical interpretation, that they really are just kind of the state space for free particles of, with a certain kind of internal spin of some kind, or generalization of that to higher dimensions. And then maybe the last case, the last example, which let's say a lot more about next semester, will be the Poincare group. And that's I'll call R31 SO31. So this is now rotation. So now we instead of using the usual metric, we take a metric with that's when you diagonalize, you have 3 positive numbers and 1 negative number, and you look at the generalization of the orthogonal group that preserves that. It's called the Lorentz group. And so here you get, what happens is you get several different kinds of orbits. Because what happens in Minkowski space, you have kind of a light cone of the things of zero, which have zero length, the light cone, or you have things that look like that, or you have things that look like this. Anyway, but you can see that there's a more interesting kind of geometry, and when you go to this, to this geometry where you've got one direction, the norm squared is negative, and then you're going to have more interesting kinds of orbits for depending on where you are, and they're going to have a physical interpretation of being time-like or space-like or light-like. There's a beautiful physical story we'll get to. And then for each of these orbits, you're going to get different little group, different stabilizer groups, and you can calculate what the orbits are. You can calculate what the k alphas are, and the k alphas are all going to be groups that we've studied. And then you can then list all the irreducible representations of the Poincare group, and they're going to be there's an interesting story about the first Casimir in some sense is the mass squared, and then the second Casimir is well. Anyway, so you get an interesting story there, which we'll get to in the second semester. But I wanted to, but these are the main cases of interest in physics. Okay, so I think I better stop here. So I haven't. The one thing I haven't said is I haven't said anything about the whole first part of what's in chapter 20. Next time. And that actually the motivation for that whole section is really kind of because of stuff I want to later do with quantum field theory. So maybe next time I'll kind of quickly say something about the motivation for why there's all this other stuff and earlier on in chapter 20. But for what you really should try and understand, just make sure you understand the story about E2 and E3, and then try and read the last section of chapter 20, which is the story that I was trying to tell you here about the general case where n is commutative, and then and see if you can try and make sense of that. Okay, so any questions right now? Okay, so if there are no questions right now, I'll cut this off, and but do please come back, and if anybody wants to talk afterwards, I'll be here for a while. Okay, so by now, and definitely have a well, whatever plans you've managed to make for Thanksgiving, despite all this, I hope they're enjoyable, and I'll see you all in a week. Okay, bye now.
Thank you. Enjoy your break.
Bye.
Have a nice Thanksgiving break.
Bye.